So as we look at the ideal gas equation, we have to look at relationships between our variables, and then we can have an equation to use and to plug into. So let's look at the mathematics of the ideal gas law. The first thing we're going to look at is pressure. Pressure is the number of collisions between the gas molecules and the container walls. That just means you have molecules pressing from the inside out and from the outside pressing back in, which is the atmosphere. So how do we affect pressure then? How do we make those collisions more frequent or less frequent? That's where we get into pressures, volumes, and temperatures. The easiest way to think about pressure is kids in a playground. You can imagine that if you have kids in a playground, they're like this little pink ball. They're bouncing around on all the toys and all the fences. So how do we change their rate of bouncing around on all those fences? The three ideas that are going to help us build the ideal gas law is going to be pressure and volume. It's going to be pressure and temperature. It's going to be pressure and the amount of gas. So let's think about these briefly, and then we'll look at them individually. When you think about pressure and volume, think about size of the playground. If you have a normal playground and then you let those children on the playground play in the field next to it that's double in size, it's going to take those kids now twice as long to run from fence to fence. So every time we double the pressure, that would be squishing those kids together in, say, half the playground instead. But if we use the example a moment ago of doubling the playground, doubling the volume, the size of the playground, that's going to cut the pressure in half. So based on the size of the playground, pressure changes opposite of volume. So the bigger the playground, the less pressure on all those toys, because now there's a whole big area for those molecules or those children to run around in. Pressure and temperature, a little bit easier to think about, probably because if kids are cold, they're not going to want to play on all the swings that are metal, the fences that are metal. They're going to want to go back inside. They're going to be wearing their big coats and not moving around very much. So you can imagine if they're hot and they're warm, if they have shorts on and tank tops on and tennis shoes on, they're going to be running around pretty fast. So high temperature means high pressure. No different than throwing an aerosol can into the fire. It's going to want to explode because of the increased pressure might breach the container itself. The molecules that are slow are going to be the molecules that are cold, and that's why basketballs don't bounce in the wintertime if left outside. Probably the easiest of the three is pressure and the amount of gas molecules. Amount of gas is really just the amount of children. If the entire third grade is out at recess and you put the entire fourth grade out at recess, you just doubled the amount of kids, you doubled the amount of pressure on all the toys and the fences. But if you have the third grade at recess and then you take half of those to lunch, you're going to cut the pressure in half because now you have half the kids. It's no different than letting air out of your tire, putting air into your tire to change the pressure. So let's look at those briefly again, but just individually this time. So when we think of volume and pressure, just think of size of the playground. Larger playgrounds will decrease pressure because those kids have to run across a larger distance to bounce off one side to the other. This is what we call inversely proportional. As pressure goes up, volume goes down. So you can imagine that if pressure goes up, if you double the pressure, that's because you cut the volume in half. If you double the volume, you're going to cut the pressure in half and vice versa. We can also look at temperature and realize that if we double the temperature, we double the pressure. If we cut the pressure in half, we're going to cut the temperature in half as a result. So faster molecules can strike those container edges quicker. And if they're faster, it's because they're hotter. Colder molecules are going to move slow. It's going to take them longer to hit the edges of the container. And that's going to reduce the pressure as well. This is what we call being proportional. So as one goes up, the other goes up. So if you double temperature, you double pressure. If you cut the pressure in half, you're going to cut the temperature in half. They increase and decrease at the same rate. Lastly, probably the one that's most recognizable based on just airing up a tire. If you put more molecules in the tire, if you put more kids on the playground, there's going to be more pressure on all the toys and all the fences. If you have a leak in your tire and molecules are escaping, no different than kids escaping from the playground, there's going to be less pressure on the playground if the kids are escaping from it. So more molecules, more pressure. That too is proportional. So they increase by the same rate, they decrease by the same rate. So twice the kids, twice the pressure. Half the kids, half the pressure. That's what proportional represents mathematically. So as we start to look at our equation, we have volume on bottom and temperature and moles on top. Now we just need a relationship between volume, pressure, temperature, and moles. So scientists worked for a very long time and they realized that the magic number for ideal gases is 0.0821 liters, atmospheres divided by moles times Kelvin. All the units we need are all the units that R gives us. So like math has pi, ideal gases have R. This ideal gas constant is a number that we can use for any gas-related question, and it'll help us cancel units. Probably the most important feature of R, though, is the units it has. If our problem doesn't have liters, you have to convert. If our pressure is in millimeters of mercury or PSI or something weird, we'd have to convert it to atmospheres before we use this equation. If we have grams, we're going to have to calculate moles from the periodic table. If we have Celsius, we're going to have to calculate Kelvin. If we don't have every single measurement given in the problem in the units of R, we're wasting our time completely. We're going to get one of those easy wrong answers. So notice up here that we have things on top being proportional and on the bottom being inversely proportional. You'll see a matching section based on that idea. But we talked about number of molecules and temperature being proportional. As they double, so does pressure. And that's what it means to be in that numerator. The denominator is volume. And that's because pressure goes down if volume goes up and vice versa. Oftentimes we rearrange the equation by timesing both sides by V. And when you do that, V's cancel over here and we get PV equals nRT. This is the one I'll give you on the exam. In this case, the final exam, last 5 questions. I'll also give you R on the exam. So if R is plugged in, you're going to have 4 variables. The problems are going to give you 3 of those 4, and then you solve for the missing one. So here's what a problem looks like. I like to make a chart, and this is kind of in chart form already to make it a little bit quicker. So you can imagine that if we make a chart, we have P missing. We have N, V, and T. We also have R, which is 0.0821 liters times atmospheres over moles times Kelvin. So again, R is going to be given to you on the final exam. You just need to remember that if it doesn't match R, we're going to have to fix it. So let's look at our units. We have moles, and R has moles. Check. We have liters, and R has liters. Check. We have Celsius, and we have Kelvin. That's a problem. So add 273, and we get 873 Kelvin. The only thing missing is atmospheres, and that's exactly what we'll get in this problem. So now that we're converted up to our standards, let's solve for P. So we're going to divide both sides by V. V's cancel. That's going to tell us that P equals N, which is right here in our chart. That's 0.10 moles. We have R, which is a constant. That's 0.0821. That's liters times atmospheres over moles times Kelvin. So that was R from our chart. We have T from our chart, which was converted to 873 Kelvin. All of those three numbers multiplied together divided by V, which happens to be 2 liters. Notice what happens because of R, moles cancel with moles, top versus bottom. Liters top cancels bottom, liters, and then Kelvin with Kelvin. All that's left is atmospheres, so it's going to be 0.1 times 0.082 times 873, hit equals, divide by 2, hit equals, and you'll get our answer of 3.68. So you'll see quite a few of those problems in the homework, and I think one of those makes it to the final exam. Specifically one that solves for N, not P. We can have some spin-offs of these kinds of problems, and that's what you're going to see in the homework, but not so much on the final exam. Molecular mass is finding N first. So you can imagine that if you have our equation PV equals nRT, if you divide RT on both sides, you can get N. So if N equals PV over RT, that's the one that's on the final exam, we can solve N. So N's going to be moles, so let's say N moles. Then we can go to the periodic table and say that in 1 mole we have grams from the periodic table, and we can very quickly get molecular mass. So you'll see a few of those problems by getting grams from the periodic table once you've gotten N from the PV equals nRT equation. Density would be very similar, but solving for V. So if you have PV equals nRT, solve for V by dividing by P on both sides. That equals V, so nRT over P. Density is mass over volume. They'll give you mass. And we just found volume. So density is mass over volume, and volume came from our PV equals nRT equation. Mass would be given in the problem. So you could just take their number they give you, divided by volume that you find, and get density of a gas in that grams per liter that we would typically see for gases. So you'll see a couple spin-offs from the ideal equation in some of your homework. The last part of this chapter is the before and after problems. We'll catch that in our last video. See you then.